Hello, and welcome to this Vivado Quick Take video, where we'll be discussing how to use multiple clock domains in your DSP system design. In this video, we will see how multiple clocks can be used in a multi-rate design, and how to view and manage multiple clock domains in Vivado System Generator for DSP. This training assumes that you are familiar with the basics of Vivado, including IP Integrator and System Generator. System Generator for DSP is a data path design environment. Blocks representing different DSP functions, like FFTs, FIRs, and forward error correction, are placed on the Simulink canvas, along with stimulus blocks, or sources, and viewer functions, also known as sinks. The data path abstracts some signals, and since DSP is intrinsically sample-based, we abstract the clocking while automating data path growth, or dynamic range and precision, from one block to the next. The data is sampled at gateways into the block diagram, and that sample time is inherited to downstream blocks automatically. So when the data is upsampled to a higher rate, the new rate will propagate to the blocks it serves. This allows a large DSP system to be simulated as a model-based design, and then automatically convert into RTL to be added as blocks within the Vivado IP catalog. A common way to get the most out of the DSP hardware design is to overclock the resources. This allows the sharing of a multiplier across numerous taps of the FIR filter. So instead of using 40 DSP slices running at 100 MHz, we use 8 DSP slices running at 500 MHz. Parallelism and folding techniques can be combined to take advantage of the FPGA's programmable logic. Since we're taking advantage of the direct connectivity between the slices, we also get the lower power advantage. But different cores have different maximum operating frequencies, so the overclocking for one section may not be advantageous for another section of the DSP system. In the RTL world, you could run each section at a different rate, each specific to their needs, with minimal handshaking or FIFOing between blocks to get the most out of the system. But an issue occurs when you want to apply asynchronous timing on the parallel processing blocks inside of System Generator. Since the clocking was abstracted and inherited from one block to the next, making a jump from one domain to the other requires us to add specific information. Let's take a look at a synchronous system and see where we can make improvements in the overclocking scheme. In this system, we digitally downconvert the incoming signal to near baseband. The incoming data arrives at a sample rate of 491.52 MHz and is downsampled to 61.44 MHz. A single by 8 decimation filter meeting the channel specifications would require an extremely long filter length and result in inefficient hardware implementations. We can reduce and reuse resources by cascading through 2 half-band filters, followed by another 2x decimation stage to implement the channel filter. This simulation demonstrates each stage's output data and final spectrum. This design uses 13 DSP slices instead of 128 for the single by 8 version. And we're taking advantage of the AXI streaming ports on the FIR compiler to easily connect multiple stages of FIR. We will abstract the handshake capabilities inherent in the AXI protocol through the automatic rate propagation delivered with System Generator. The FIR output is gain controlled through the PowerScale processor register, as shown in the previous Quick Take video, specifying AXI 4 Lite interfaces for your Vivado System Generator design. Now let's take this design and modify it to take advantage of multiple clock domains. We will convert this design to have a total of 3 clock domains for this system. I've added a couple of hierarchies to help with visibility. In our current example, the PowerScale register is synchronous to the DDC processing domain. It can be advantageous to place the registers on a separate clock domain, which is asynchronous to the DDC processing domain, but synchronous to the ARM or Microblaze common peripheral domain to reduce resources at a system level. The DDC output data has a sample rate of 61.44 megasamples per second. But this sample rate is achieved by using clock enables on the 491.52 MHz system clock domain. Complex IP within System Generator, like FIR compiler or the FFT, can process data so that the sample rate is not equivalent to the clock rate. This means all of the DSP slices within the 3 FIRs utilize multiply accumulates that process data at 491.52 MHz. But folding techniques automated by the FIR compiler generate appropriate input and output sample rates by reusing those resources. If we move the final data from the clock-enabled rate to an actual 61.44 MHz domain, it would allow easier connectivity and design when subsequent blocks are connected. An example of this is shown in the QuickTake video using multiple clock domains in Vivado IP Integrator, where the DSP block is fed to a high-level synthesis block, which acts as the hardware accelerator for the ARM processor to calculate new power scale values. We will need to safely cross the data between the processor, DDC, and output domains. The FIFO is the ideal block to help here. Since the processor domain is slower and updates its data to the power scale register infrequently, only a small FIFO is necessary to absorb the handshake control signals and data. And since we will make the 61.44 MHz output domain with the clock manager for the 491.52 MHz domain, a small FIFO is all that is needed for this domain crossing too. To utilize multiple clock domains, we'll take advantage of the subsystem capability inherent in Simulink. Each domain will have all logic associated with its clock domain within the subsystem. We'll start by placing the gain control and gateway out blocks into their own level of hierarchy. All logic in this section will operate at 61.44 MHz. A FIFO will cross the data from the DDC to the new M-axis domain. Connect the DN and WE signals on the FIFO to the DDC outputs. Connect the DOut and empty signals from the FIFO to the M-axis inputs. Since the empty signal is driving T-valid, we actually need to invert this in the M-axis domain. Also, we'll drive the read signal from this inverter so the FIFO will always read data and mark it valid whenever it's available. Since the FIFO has a read latency of 1, we need to delay the inverted signal driving T-valid by 1 cycle. Finally, we connect the FIFO read signal back to the FIFO at the top level. Next, we'll place the power scale register in its own level of hierarchy. A relational and delay block are used to synchronize a strobe signal that we can use as the write enable for the FIFO whenever data changes. Another FIFO is used to pass the control register to the M-axis domain. Similar read logic is duplicated for the power scale register. Since the data is quasi-static, I don't care when it becomes valid, only that it automatically gets updated and used by the gain control block. Connections to the FIFO are made at the top level. The rest of the DSP data path is moved to a separate hierarchy too. At this point, our model can be simulated as the synchronous design to verify correct functionality before we move to the final multiple clock domain. The FIFOs act across the data between the domains and will exist at the top level. Currently, the only other block which can act to cross the data is the dual port RAM, which is very useful when passing banks of registers or addressable data. All other blocks, excluding the top-level system generator token, should be located in a lower level. The top-level system generator token has a new feature added in Vivado 2014.1 on the Clock tab, as shown here. When Enable Multiple Clocks is selected, System Generator will look into the underlying systems to find individual tokens specifying the clock rates for each system. On this block, we see that the Simulink system period and the FPGA clock period in nanoseconds have both been set. To enable multiple clock domains, we need to change a setting on the clocking tab for the top-level system generator token. Each of our lower domains will have their own system generator token to identify their clock requirements. The control domain token gets set for 100 MHz. Commonly, the processor system will be operating somewhere between 50 and 100 MHz. The gateway and sample period must be changed too. The DSP domain gets set for 491.52 MHz. And the M-axis output domain is lowered to 61.44 MHz. Updating the system shows that we have no errors. Now that the other domains are set appropriately, we'll simulate and verify our results. But first I want to add another signal into the waveform viewer to help us debug between the three domains. Let's select our data value in the output domain and add it to the list of signals in the viewer. We'll also add the output signals from each FIR. After simulating, we see that the design functions as expected. Each clock domain in the waveform viewer is denoted by color. Selecting the clock in the waveform cross-probes into each domain, and this also enables cross-probing with each signal. For more information, please see the Xilinx View Signal chapter in User Guide 897, Model-Based DSP Design Using System Generator. Now that we have the optimal system, it can be exported to RTL or the IP catalog. Here I'm exporting our down-converter to the catalog by invoking the System Generator token at our top level. We'll set the compilation target to IP catalog and also set the target directory where we will place the IP. After generation, we can add the IP subdirectory to the user repository. This gives us the same accessibility to the IP in either RTL or IP Integrator as any other Xilinx IP. As we investigate the packaged IP and IP Integrator, we note that all three clocks are brought out to the IP for easy connectivity to clock managers or other sources. Vivado and System Generator support multi-rate design for Xilinx all-programmable devices. Using multiple clock domains in your DSP system design allows you to safely pass data between domains, while increasing design usability and reducing power. It can also reduce resources by allowing filter chains to easily operate with higher performance while utilizing folding techniques. For additional information, you can view the related QuickTake videos specifying AXI4 light interfaces for your Vivado System Generator design, and using multiple clock domains in Vivado IP Integrator. More information on instructor-led training can be found on Xilinx.com, along with 2 user guides, UG897, Model-Based DSP Design Using System Generator, and UG994, Designing IP Subsystems Using IP Integrator. Thank you for watching this Vivado QuickTake video.